We have a final next week, Thursday. I think it's 9:45, but for those who have a conflict with MMC, I will try to be here at 9. It's me hard to wake up, but I will, so you can take it earlier. Okay? You have the review in Dropbox, and today I will go over the material. I just need to finish the unit. Whatever we do today, you don't have to worry for the final. It's just interesting physics. Okay, let's go. So we talked about conservation of momentum. I was blocked because I show you this video, but you know what? I crop it out. Like I remove a little piece before, a little piece after, and they didn't detect it, so I was able to upload the video. So it's in YouTube. My lecture. Okay, so a lot of application of angular momentum, conservation of speed. So for example, this is the Kepler second law, right? And he was able to show it using data. So he used the position of Mars. So first he had the position of Mars as seen from the Earth and doing crazy math using geometry. He was able to plot the position of Mars as seen from the sun. So anyway, he was able to show that any planet orbiting the sun is going to go over an ellipse, and it's going to go really fast, and then it's going to slow. So he calls that the equal area law during the same amount of time. So during the same amount of time, a planet will cover always the same area, right? Okay, so it's going to speed up, and then it's going to slow down, and then speed up, and then slow down. And then Newton was able to show this law, so second law of Kepler's planetary motion. He was able to show it by using conservation of spin. So if you speed up, because the mass is closer to the axis of rotation, and then it's going to slow down. Okay, so conservation of angular momentum can be very interesting indeed. So if for the same mass here and for the same muscles, okay, so the same torque, it's going to be much easier here than it is there, because when the mass is moved toward the center, the axis of rotation, inertia goes down. So you could show that in 2010, there was an earthquake in Chile. It's a terrible earthquake that actually moved the distribution of mass about the axis of rotation of the Earth. So everything went farther away from the axis of rotation, and the Earth started to spin a tiny bit slower. So it's a tiny bit, but nevertheless, it was measurable. So it was like 1/26 millionth of a second. Okay, so that was a big earthquake in Chile. So it's like the Earth, instead of being nice and spherical all the way around, it was a little bit elongated here where Chile is. Good morning. Okay, so again, if you have a pop quiz question for this one, the solid sphere arrive first, and I will try to trick you. Okay, if you have all cylinders but different masses or different sizes, turns out it does not matter. They all reach the ground at the same time, because here it's like in free fall. The mass does not matter. So even though it's not falling straight down, gravity is diluted. It's g times the sine of this angle there. So if they all have the same shapes, it's all cylinders, all sphere, all rings, they reach the bottom at the same time. Now, if you have a race between a sphere, solid sphere, a cylinder, or a ring, first comes the sphere because it has more mass packed around the axis of rotation. Second comes the cylinder, and last comes the ring. So there is one pop quiz question. Make sure you don't get tricked. The mass, if they have the same shape, if they are all cylinder or all rings or all spheres, the mass doesn't matter because when you do the computation, it cancels out, and the size also cancel out. Okay. Conservation of spin. If you have this in some science museum, right? So if you have a kid here and the kid moves in, what's going to happen to the platform? Spin faster, right? It spins faster because you're going to have more mass toward the center. So it's really cool. Here's another application. If you jump here, you crunch, you decrease the moment of inertia, so it's going to spin faster. You extend it, you slow it down. And that's a joke. Hopefully you get the joke. Okay, so bathtub, here you have a sink, and we can describe that in terms of a vector field. So we call that a sink. So anyway, if you have a bathtub here, it's going to spin faster over there because of the conservation of spin. When it gets closer to the center, it has to spin faster. If it's an isolated system, there is no external force. Formation of the solar system, same idea. In this direction here, there is no spin to begin with, so it's going to be flattened out because of gravity. But in this direction, you have conservation of spin. So some of the pieces here will be in balance between the centrifugal force pushing out and gravity pulling in. So it's going to stay in a circular motion. But at the center, as things, gravity is, let's say, win the game. But as it's going to be pulled toward the center, it's going to move faster. Because it's moving faster, pressure increases, temperature increases, and you're going to start fusion. Hydrogen into helium, you have a sun, right? So it's that's the formation. That's called the nebular hypothesis. How planetary system can be formed, and we found many of them, right? It's not just us. Okay, so you can do those math. Those math are easy. Look, it's an easy demo. You take a tube, for example, and a string. If I don't tell you that I watch your demo, you have to remind me, because right now I have so many emails that I'm losing track of everything. So make sure you can send me an email again if you send me a demo. So this is a tube here, could be like Home Depot, like a tube, like copper. You have a string and you make it spin, and as you pull the string here, it's going to spin faster, because even though you are applying a force, you are not applying a torque. Okay, it's a force, but it's not a torque. The torque equals 0 because it doesn't make it spin faster or slower. So it's isolated in the sense that there is no external torque. You can show this equation very easily, very quickly, because I want to get to reviewing the exam. Okay, so the angular momentum I1 omega 1 before equals angular momentum after. So it's like, remember, M1 V1 equals M2 V2, except you have in collision, but it's the same idea here. So inertia just for a mass is just M and then the radius square. Omega is just the velocity over R1 equals mr2 squared times v2 over r2. I go bye bye, bye bye, bye bye, bye bye, bye bye, bye bye. v1 r1 equals v2 r2. Okay, not just for you. Okay, not using it for the final. Okay, merry-go-round, blah 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 blah. You have all those problems that you can find in your textbook. So if you go into engineering, I recommend that you try to do it. As long as you understand the concept, everything else is algebra or easy calculus, so not to worry about it. So angular momentum is a vector. How do you find it? You take your right hand Why is it a vector? Because it's proportional to the angular velocity, which is a vector. So you take your right hand, if the spinning is this way, the thumb will show you the angular momentum vector. So you have very interesting things happening. So I told you about that. If there is angular momentum, okay, the vector wants to stay in the same direction. So if you have angular momentum here, spinning, right? So it's very hard to change that angular momentum because it's going so fast. It's spinning so fast. So if you want to deflect the bullet, you need to have a torque applied, but a strong torque because the angular momentum is so strong. Okay, so the torque changes the angular momentum, but the change depends on inertia. And so in this case, you need a very large torque to change the angular momentum because the angular momentum is so large because it has a very, very, very high speed. Okay, you can do that with this. Okay, very hard to stop, large angular momentum. And then you can take it to calculus. You have a cross product. That will be the formal definition of angular momentum. It's a cross product between R and P, the momentum. So you have to do the right hand rule. Don't worry about it, but it's a cross product. So the angular momentum of a mass depends on the origin. So you need to decide of the origin, and then you compute the angular momentum relative to this origin, except if we are talking about the angular momentum of the center of mass. So in that case, it doesn't matter. The origin doesn't matter. Okay. So interestingly, angular momentum is a vector. So I was trying to do the demo with him, who is not here. It didn't work well because of friction. And then someone else came up, forgot who, and she stand up, and she was lightweight, and it worked, right? So it's because if there is no static friction, you don't want static friction, you don't want kinetic friction for that to work. But you see, angular momentum to begin with is up, so it wants to stay up. So if you flip the wheel, okay, it get very upset because it was up. I want to stay up. There is no external force. I want to stay up. So the stool here start to spin in the opposite direction. So when you add them up, you're gonna get what you start with. So it's like the story with John Kennedy. Right, the assassination. So the momentum is a vector. I can show you that very quickly. Momentum to ride on a bicycle. I spin this wheel up, get it going really fast. I never had any momentum in this bicycle because it's spinning around and around the entire wheel of angular momentum. And it's so happens that if I try to turn the wheel a new way, it will fight against me. It won't let me turn it just a little bit. And it turns out that because it has all this momentum, it actually helps you stay upright when you turn your bicycle. And it keeps you from falling down once you get moving. And I can also use this to turn. So now I can use that angle now on the bicycle hill to fit myself on when I'm on top of the flat. I turn the bicycle wheel. Isn't that good? Turn it straight, I stop. I can spin back the other way, one way. The other way doesn't work because there is always a preferred direction. It's because of the friction. You see the cool shoes? Conservation of momentum. Yeah, I told you, right? If you spin, you are in the water, you do this with your arms, your body will do the opposite direction. You have the same effect with this, right? This conservation of spin. If I don't know which one is easier to do. I guess if you spin your body in one direction, the skateboard will spin in the opposite direction because of conservation of spin. So that's a famous move. It gets very hard to do. And knee boarding, same way, you spin your arm in one direction and the board will spin in the opposite direction to make sure that momentum is conserved, right? And one very cool thing that I have found, it's biking. When you have a bike, not that I bike, I mean I bike, but not motorbike. So the space telescope, so in that case it's James Webb telescope that was launched in 2021. It has reaction wheel inside. So if you want the telescope to move in one direction, to be back, like the sun doesn't hit it, then you have a reaction wheel that will spin in the other direction. That's what they use in space station.
Spacecraft without using a rocket, just like cats do. You should probably go back and watch that too. And I like to think about reaction wheels is motocross. This video from way back shows it pretty well. So a motocross racer goes flying up into the air and it briefly kind of waves like a spacecraft, but riders are able to control whether the nose of the bike goes up or down by braking or accelerating. If they accelerate the back wheel, the nose goes up because the reaction torque spins the bike in the opposite direction of the wheel. And if they want to pull the nose down, then they hit the brakes, and all the torque of slowing down the wheel is redirected into the bike and it tilts down. Basically, it's the same idea on a space telescope, but instead of attaching motorcycles to it to turn it in different ways, they have little electric flywheels that are always spinning, and if they accelerate them or decelerate them, the angular momentum is transferred to the telescope and they can spin and point the spacecraft very precisely in all sorts of directions using a combination of reaction wheels oriented in different directions. The other thing that's fascinating about the James Webb Space Telescope is we're trying to keep it oriented in a very specific direction.
Okay, so I thought that was a very cool application if you do motocross.
And getting all this pressure on this.
So the same way you can transfer linear momentum, you can transfer angular momentum. You can transfer spin, but it will spin in the opposite direction. So super cool. And then last, it's the cat. Okay, so that's the same thing here. You can go there if you're interested. And the cats are very smart. They know physics somehow. And if you hold a cat by its leg, it will know what to do. It will spin the tail in one direction, so the body will spin in the opposite direction because of conservation of spin. Not only that, the body, of course, has more mass, so the cat knows that it has to crunch. He crunch the upper body here, spin in the opposite direction, and before landing, it will extend the legs, right? So I told you, very, very, very smart. Okay, do you see a cat somewhere? Do you see my cat somewhere? Because of course, if I'm looking for okay.
Hey, it's me, Death, and welcome back to Smart Every Day. So you probably observed that cats almost always land on their feet. Today's question is why? Like most simple questions, there's a very complex answer. For instance, let me reword this question. So cat goes from feet up to feet down in a falling reference frame without violating conservation of angular momentum. Now, I've studied free-falling bodies, my own in fact, in several different environments, and once I get my angular rotation started in one direction, I can't stop it. Today, we're going to use a high-speed camera. We're not going to use Alec, because this is my daughter's cat. Don't hurt it. We're going to use a skunk cat. Let me introduce you to Gigi, the skunk cat. Let's flip the video vertical, and then contract the cat. It'll take a lot more effort. So we're going to try to do it in a way that doesn't make me like that. That's pretty hard to do. Yeah, cat.
So if you have a cooperative cat, you can try it.
Okay. Oh, wait, so you done. You done approved. Here's getting drink water. So here's what's interesting about this scene. You'll notice at the beginning of the drop, it's not rotating. Halfway through the drop, the cat is rotating, and then at the very end, Gigi somehow stops rotating. Newton's first law says that an object at rest will stay at rest unless acted on by an external force. I see no external forces on this cat. So what's happening here? It's not making sense to me. Okay, so in order to really get the right name, we're gonna have to draw over 90 degrees out of base. Girl, this time watch your tail. 3, 2, 1.
Oh, cat.
So you figured it out. Check this out. You probably have her tail is rotating in the direction opposite where it was rotating. What's interesting about it is that it's not reverse. In fact, you can bobtail cats and do this. It's called the cat riding reflex. I'll prove it to you. I came across this video from the 60s when the Air Force was researching microgravity for future asteroids. Turns out they took some cats out on parabolic flights. He tries to rotate his tail with his foot, but it doesn't work. He just ends up mutating. Wow. I think that's something interesting. He takes his back and he bends it. When he bends his back and then creates motion, something interesting happens. Oh, I know I'm getting somewhere. So let me show you one more cat clip with the mirror. We'll figure this out. Yeah. Exactly. It's a long attention. I found something pretty cool about cats. You don't know? Okay, game done. If you would, go check out your other cat videos after trying to catch Gigi. Looks around it. If you
So it's a very nice channel. It's called Smarter Every Day. So there is this channel, and you have Veritasium also, which is a great channel. Plus, they don't block me on YouTube, so I appreciate that. You see, it's always a trade-off between the torque and the displacement. So it's like when you are biking low gear or high gear. So small torque here, but big displacement equals big torque and small displacement, right? So he does two things. He crunches his body, this body here, to decrease the moment of inertia, So that way the torque balance out, right? So it means the angular momentum will be conserved. So a lot of very cool applications. So the same way that you have the net force equals dp, so p is the momentum over dt, so that's the calculus form, that's how Newton derived wrote his Newton second law. You have the same thing for torque, okay? So the net torque equals the derivative of the angular momentum. It's the same thing, okay? So if you apply a torque during a time t, the momentum will change. How much will change, of course, depends on the moment of inertia. Okay, so you have all those very cool applications. For example, okay, another thing that you have to remember is that the torque can change the spin rate, make it go faster, slower, or change the orientation of the spin. So when you do this with your bike, you are changing the orientation. The vector now it's going to be this, and the wheel just turned on its own to the left. Okay, so you are not changing the spinning rate, you are just changing the orientation of the spin. Okay, so this is not obvious, but if you explain it this way, it makes sense. Okay, so a torque can make something go faster, spin faster, slower, or change the orientation of the spin. I like to explain it this way because sometimes they explain with the torque and the angular momentum, it's confusing. I think this way is much better to understand. And same idea if you are doing counter steering, you push this way, the bike will go that way, and then it will go this way. So you're making a turn left. Okay, so here they explain it with the angular momentum being changed because you're applying a torque. But you can explain a different way. But if you are interested, here you can learn about. So this is used in race, motorbike race, because the handle here is fused. So you have to use counter steering. You don't have choice. Okay, so I highly recommend that if you want to do in more details, you should what should you do? You have to open your textbook. That's what you should do. Okay, so ouch, and then remember we have a pop quiz. Okay, so let's review for the final. I'm partially blind. Okay. Let's see if I remember everything. So the remember the work. So I told you don't worry about projectile motion or linear kinematics. So you have the work kinetic theorem. It's also conservation of energy. So it depends. You can use both approach that say that the net work. Okay, so it's the net work, and work is force times distance, but it's only on. It could be tricky. So let me finish with that. Will be equals to the change in kinetic energy. The change in kinetic energy is 0.5 times the mass final square minus initial square. So the net work, either you say it's the sum of an individual work by each force, or you can say it's the net force parallel to your displacement times the displacement. Okay, so you can do it two ways. Now you have to be careful that, let's say you are pushing a mass here on the ground and you have a force here, let's say applied force. and you want to know the work done by this force over a displacement delta x, you cannot use F. You have to use the component here, the parallel component, right? It's the dot product, right? Okay, so the work done by F, and it's always the work done by F on something. So here it's on the mass, will be the parallel component times the displacement. And remember how we found component. You start from the tail and you go to the head, right? You can always think that you have a cross here at the tail. Okay, this is your point. It's a vector. You see, this is your x. If you want, that will be your y. So you have to be using the parallel component. Okay. And the other thing that you have to remember is that the work done by friction, so it's always kinetic friction, because static friction doesn't move, so there is no work. But the work done by friction on a system is always negative, because it's taking away, it's trying to slow it down. If the speed does not change, that means that the net work is zero, so there is no change in kinetic energy. Okay, what else you have to remember? You have to remember that, what else? So the network, for example, the network, okay, could be equals to the work done. So let's say you are pushing a mass here and you are doing your free body diagram, and you do have some kinetic friction here. Okay, and in magnitude, kinetic friction is the coefficient times the normal force. The normal force, you have to remember, it depends. It's you have to do everything up, it goes everything down to find the normal force. For example, if you are pushing into the ground, so the normal force is not just the weight. Okay, so in that case, because you are pushing on the ground, the normal force will be the weight plus that component here. Agree? So remember, you have to feel like the ground is feeling. The ground has emotion, right? So it's like it's little spring here. So anyway, so the net work will be the work done by the applied force, right? So the force applied on the system plus the work done by friction, and that will be equals to the change in kinetic energy. It's just a way to do. You can do conservation of energy as well. It's the same thing. So anyway, my point is that you have to be careful here. That will be the parallel component times delta x, and that's going to be negative. That will be negative. So it's going to be the kinetic friction, in that case, delta x. Okay? Now you could write it using conservation of energy. You could say energy before equals energy after. So it will, energy before will be the work done by the force. Okay. So energy that you put in the system minus the work done by friction. So minus the work done by friction plus kinetic energy before will be equals to kinetic energy after. It's the same thing. This is conservation of energy. So doing work means you add energy to the system. Okay, it's like you have a reservoir here, you have some kinetic energy to begin with, and you add stuff. And then some friction will take away some of the energy. Okay. Okay, so friction, remember that if you are doing friction, friction is not a conservative force, right? So if it's, this is the ground, and you push, you are pushing. So this is a view with a drone above. and you push and you push and you push and you push and you push, and for some reason you are doing a workout here. Okay, you push just to work out. The work done by friction is not zero because friction is a non-conservative force. Okay, so the work done by friction will be negative, the kinetic friction times the linear distance. That's a linear distance because you can measure with a string. But if you take the mass, so now we go up and down, you take it this way and that way and that way and that way, and you are above the ground. This is the ground here. Yeah, look at this. The work done by gravity is zero because the work done by gravity is because gravity is conservative. So the work done by gravity is just the change in potential energy, which is mg delta h. So you see this is initial and this is final, and there is no change. So it's a conservative force. All the forces that derive from potential is conservative. Huh? Right? Okay, what else? Uh, just to make sure you know how to use your TI, the gravitational force between two masses, so M1 and M2, so it could be you and the Earth, or it could be the Earth and the Moon, for example, so you have a distance d. The gravitational force between masses and that's the universal law found by Newton, who was a genius, proportional to the product of the masses divided by the distance square. The distance he was able to show that for the Earth, for example, it's really the center. If it's homogeneous here, about homogeneous, it will be the center. You take the distance between the centers of the two objects. It's an inverse square law. Multiply the distance, the pool will be divided by 4. And it doesn't matter, the force here is always the same because for every action, you have an opposite and equal reaction. So it's the same force, not the same consequence. The moon is moving and the earth is moving, but wobbling tiny bit. So consequence is not the same, but the force is the same. Impulse, same thing. G is a very small number, is 6.67 times 10 to the 11, whatever. That means gravity is very weak. You need a lot of mass to build up enough to feel gravity. Otherwise, it's very easy to defy gravity. That's why we can stand up. Otherwise, we will be crawling on the floor.
Will you give us the gravitational constant, or should we just learn it?
I forgot.
Right here.
Oh, God. Remember, I put in announcement, right? The equation sheet. I won't have any. So you have to print out your equation sheet. Make sure that you have everything you want. Everything else you memorize. It's good. It's good for the brain.
Professor, can I ask?
Yes.
Why don't I cover the same topic as Tesla?
I'm doing it right now. I'm going over it. I told you to skip linear and 1D and 2D. So you can go over test 2 and test 3 and assignment. So no linear kinematics and no projectile motion. Okay, definitively a problem with okay, that's the word I cannot say. The ladder. Okay. Ladder problem because it's a classic. I forgot, but you have to use the torque equilibrium and you have to use the force equilibrium to make sure it's a static equilibrium. You can have a force equilibrium, like if you are driving. If you are driving, you see it's a force equilibrium, but it's not a static equilibrium because there is some spinning. Okay, so you have to use both. And for the torque, you use the lever arm. Okay, I did that in a video or in a lecture. If you use the definition of the lever arm, it's much easier. I forgot. the problem, but you always have static friction here, obviously, because otherwise it's going to slide. And of course, you don't want to go over the maximum static friction, which is the coefficient times the normal force. In that case, we're talking about this normal force here. Once you go over, it's going to slip. So you have regulation in construction. There is regulation between how far from the wall you have to put it, because otherwise if you go up, 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 at some point, boom, you go over the maximum static friction, and that hurts. And you have a normal force here. You don't have friction usually there. You could have, but you don't have to. And then you have either you have the weight of the ladder here, or sometimes you have someone on it and you have the weight of that person here. Depends on the problem. Yeah, there was one problem. There was a guy and the ladder didn't have mass. Sometimes it's just the ladder that has mass. Obviously, you want to do the computation when you have someone on it, so no, otherwise. Mhm. Okay, and then you put your name and everything. Okay, don't ask me when. I don't know. Okay. Thank you so much. Have a good day. Thank you. You too. And then definition of power. Power will be average power. You want to review that average power. You have different way, two definition. You can say, okay, that will be the net work. Okay, so it's power is the rate at which energy is consumed or produced. So it's the change of energy. Energy in transfer is the work over the time. So how fast energy is being burned. So difference between, I don't know, Lamborghini and my own day, for example. Obviously not the same power, 800 horsepower versus 50 horsepower. So it's a time. Now, if you do the computation, you could also say this is the work, the work, that will be also the force times the average speed. Yeah, that will be another definition, which is uh, because the work is the net force times the displacement. If you divide by the time, that will be the average speed. So sometimes it could be useful. So then power will be, so work is mass times, I mean, the force is mass times acceleration times the average speed. So I can write that as acceleration is the final speed minus initial speed divided by the time. Okay, different way to write it down. Average speed, remember, if it increases at a constant rate, so if the acceleration is constant, I can also say that's another definition of average speed. Right? Makes sense? Because if the speed increases at a constant rate, so the average will be, it will be at the center. That will be the midpoint here. So anyway, you can write it this way. And remember your algebra class, a minus b times a plus b is a square minus b square. So you can write that as uh, mass, and then that will be v final square minus v initial square divided by 2 t. So what do we have? That will be 1/2. So that will be 1 half m v final square minus v initial square is the change in kinetic energy over the time. Makes sense because anyway, I didn't have to do all that because by definition, the network is the change in kinetic energy and then you divide by the time. But sometimes some problem try to confuse you. So network is the change in kinetic energy. Okay? Okay. Mhm. What is okay? Conservation of momentum. I don't know if it's maybe it's test number 2. I forgot. So the only difficulty here is to remember that momentum is a vector. It can be positive or negative. So we only worry about 1D but if you are in engineering, I recommend that you open your textbook and you try those 2D. Because 2D is the same concept, but it's more math. And more math is important if you want to be engineer. So 2D or 1D, same concept. So momentum is a vector. So you have m1 v1 plus m2 v2 equals m1 v1 prime plus m2 v2 prime. So you have to be very careful because if you have a heads on, forgot. Oh, anyway, I forgot. It's okay. So if you have something like this, I don't know, heads on collision, you see that the V2 will be negative. So you have to be careful, right? So if it's moving at 3 meters per second, that's just the magnitude. So in your computation, you have to do minus 3 meters per second. So if you don't do it, you're going to add instead of subtract. And in the multiple choice, of course, you're going to take this in account. So you have to be careful with that. Okay. If it's an elastic collision, so if it doesn't stick, if it bounces off, the relative speed stays the same, right? I forgot if there is this or not, but in the assignment you have something like this. If this is only elastic, meaning it bounces off, meaning the kinetic energy is conserved, fully elastic. If they hit and stick, the final velocity is the same. If they hit and stick, right? Hit and stick, the final velocity is the same. Okay? Conservation of momentum, you can have a recoil situation. So recoil situation is when nothing is moving before. So it's like firing a gun, for example. So you have before nothing moves. And so the total momentum before equals 0. And then they push on each other, for example, or the rifle move back and the bullet move forward. So you have V1 prime and V2 prime. So this is a recoil situation and there is a magic equation, but you have to be careful to use it the right way. And there is a minus and V can be a vector. So you have plus here and minus there. There is a minus here. There's a minus because if one goes in one direction, the other one will go in the opposite direction. And be careful that the 2 is here, but the 1 is there. Or you do it the long way. You say 0 before equals m1 v1 prime plus m2 v2 prime. And velocity are vectors. So that's a recoil situation. You cannot push without being pushed. You cannot push harder than you are pushing. Consequence is not the same. The velocity will not be the same. Twice the mass, half the velocity. Okay. What else? Gravitational field G. Okay, the gravitational field is by definition that constant again times the mass over the distance square. That's a gravitational field. So for example, if you have the Earth, see you have gravitational field. If it's close to the ground, it's going to be 9.8. So G equals 9.8. But as you move away, you see it's a vector field. Gravitational field is going to decrease. And very far away, it's going to be 0. So it's given by that equation. It depends on the mass of the Earth. There is a field, it's like an aura. And if you place a mass in this aura, it will feel it and it will respond by a gravitational force. It's a vector field. And then Einstein came and said, it's no, that there is no such thing, right? He said that it's space time, the fabric of space time being curved here. Right? This is the Earth. And we are in the gravitational field, so it's space itself pushing us toward the Earth. And this is just an approximation. But that's another story with another professor in the future. Okay? So it's just an application. I mean, you just plug it in. Okay, remember centripetal force, centripetal. So each time there is a curve, you need something to provide the centripetal force. Centripetal force is mv squared over r. The centripetal acceleration is v squared over r, and it's toward the center. So it's not really a force. That means that something has to provide that centripetal force. So if you have a roller coaster here, it's making a curve, right? So that means if you don't want it to go off tangent, okay, so you need something to provide that centripetal force. So you need a winner toward the center. So here you have the weight, and then you push on the track is pushing back on you. But you want to make sure that the weight has to be larger because it's the winner, because the larger force has to provide the acceleration. So in that case, you're going to have mg minus the normal force equals mv squared over r, and that will be the curvature here that you have. If the normal force is 0, then poof, off tangent you go, and you make a projectile motion. Boom. Now, if you are like this, if it's like I show you like someone doing this, the guy was running like this, you have to run fast enough here. So in that case, the weight mg, and you have the normal force here. So both of them are providing the centripetal force. And if L equals 0, boom, you fall. So that's for the free body diagram. You always take acceleration to be positive, it helps. So that will be plus acceleration. Right? So if you are driving, for example, and speeding up, but there is a curve, so you have two acceleration. You have the centripetal acceleration this way, and let's say if you are speeding up, then you have the tangential acceleration. So if you want to find your total acceleration, you need to combine them together. So this one will just provide the staying on track, and this one will be proportional to the thrust. If you are slowing down, then the acceleration will be here. So proportional to your braking, because you slow down. Okay? Okay, you should be ready for vector calculus. Right? We did a lot of calculus stuff. So Newton's second law, F equals ma. But Newton in Principia didn't use that notation. He said the change in momentum equals force, average force, times the change in time. Or we can say dp over dt. Okay, so if you apply a force during your time t, the momentum will change, or if there is a change in momentum, then there is a force applied. So if you crash on the wall is gonna apply a force on you. So this is called the impulse. It's like a kick. For every impulse, you have an impulse back. And this is the change in momentum. And we're talking about vectors. Okay, so a change in momentum by definition is going to be the mass times the final velocity minus the initial velocity. And it's a vector. Right? It's like when you climb on the wall. Some people, they can climb on the wall. Yeah, so you push on the wall is going to push back this way, and you have friction this way, so the wall is going to push you back this, so it's going to make you go up. The change in momentum will be up. That will be your change in momentum. So it's a vector. Okay. Okay. Yeah, simple torque equilibrium. So you for the torque you have two definition. So some if it's easy, you just say, okay, it's the perpendicular component times the distance to the axis of rotation, or you can use a definition with the lever arm. Right? You can go back to this, or really, if you are you feel calculus mood, you can do the definition with the cross product. So you can have something very simple, like the athlete, an athlete, for example, throwing a, we did that in class, like something like this. Okay, so you have, I forgot, but something like this, you can look back. Because you have a muscle here and then you have the load there. So one wants to do clockwise, the other one wants to do counterclockwise. Something like this. You have to remember how to do it. And then you have the mass of the arm. So you can write that the sum of the counterclockwise torque equals the sum of the clockwise torque. When you are using this way, you have to make sure there is no negative sign. This is just magnitude. It's like saying everything up equals everything down. It's just magnitude. If you want to use negative, okay, like the book is doing, then you have to write the sum of the torque equals 0. So some of them will be positive, some of them will be negative. Or you can say the sum of the forces equals 0. So some of them will be negative if it's down or positive if it is up. If you are using this way, no negative, right? It's just magnitude. So that means the torque that goes into the board, okay, because you use your right hand with the thumb, will be balanced out by the torque that goes towards you, like this. Okay. What is okay? By if I have some, I wrote something wrong before. So the average power, yes, is the force times the average speed. Now, if I write it this way, the calculus way, that will be the instantaneous power. It's not the average. So you can go back to what I said before. If I use that definition, it's the definition of the instantaneous power. So the power at a given time, and then you have to derive. Okay, this is the definition uh, for the average power, and then you take the average velocity, and sometimes it could be the change in kinetic energy over the time. This is the definition for instantaneous power. There is no average. I don't know why I said that, but that means it's a derivative. So it means if you are given as a function of time, like something like this, I know I'm just making things up. You take the derivative, you need to take the derivative, right? So 60 plus 2, and then you give a time for t, like t equals 2 seconds, and you have the instantaneous power. Okay, so this is a definition for instantaneous power. Average, yes. That's for calculus, just for the fun. Okay. What is? And then I forgot. I forgot. Well, again, network. Okay, remember that it will be the applied force, for example. We already did that. Minus the work done by friction times the distance. Okay, that will be equal to the change in kinetic energy. We did that already. Okay, static equilibrium. Again, sum of the torque equals 0, sum of the force equals 0. Like we have the ladder. You're gonna have something with a beam because it's a very famous, it's a classical, right? You have a beam. So in that case, the system is the beam. So always in physics or engineering, you need to define your system. I don't care here that the system is the beam itself. So if you look at the force here, the tension is one force, and then if you have someone on the beam, then maybe you have the mass of the beam itself. Maybe you have someone standing on it. And then because here it's you have a bolt, like something is attaching, so you have the normal force. I call that the normal force, and then like static. I call that this way, but Usually in engineering, they don't call it this way. They say they combine them together and they call that R. But anyway, when you do the computation, you have to decompose, okay, into two components. So you can call that R sub X and R sub Y. Yes? So force equilibrium, everything to the left equals everything to the right. Everything up equals everything down. This one also has to be decomposed in two components, the Y component and the X component, right? You go from the tail to the head, you have the Y component, you have the X component. So you see that to the right here you have R sub X, to the left you have T sub X, up you have T sub Y and you have R sub Y, down you have mg and this mg here. But you will also have the torque equilibrium. So you can start with the torque equilibrium. You can go back in the YouTube and find how I did it. So we usually you take the fulcrum here. So you get rid of those. Okay, because if you take the fulcrum here, the torque applied by Rx equals 0, the torque applied by Ry equals 0. So you just have to worry about the torque applied by T sub Y. So that wants to make it what? Counterclockwise. This one wants to do clockwise and clockwise. So counterclockwise, you have T sub Y times the distance here, so that will be the total distance, equals the torque applied by mg plus the torque applied by the guy, I don't know where he's standing here. Okay, so in that case, you can use the Y component, or you can use the lever arm. There is no torque applied by Tx, because you are pushing into the fulcrum, so you are not making a rotation. Okay? Right. What else? Okay, Newton third law. For every action, you have an opposite reaction, even though it's not intuitive. So if you have a bike colliding with a truck, the force is the same, not the consequence. Okay. And then I invite you to go back to this lecture because I'm not going to do it, but rocket equation. In your textbook, it's very well done. They have two solved problems. I did it in class as well. I explained it's a consequence of conservation of momentum, but with the mass of the rocket changing with time. So there is a amount of fuel that is burned. So you can define the rate at which the mass of the rocket is decreasing. Okay, so the rocket equation, it's in my slide, it's one of the lecture, and it's in your book. So one problem about that, you can go to your book, textbook, and it was also in an assignment. And probably it's in the video. Okay, pendulum, it's a classic too because it's conservation of energy. Okay, you start with potential energy. So potential energy depends on your reference level. So here you can say potential energy equals 0. So the change or the potential energy before. So before it has potential energy mg delta h. And all that energy is going to turn into kinetic energy. Okay, so this is conservation of energy. And then, of course, don't forget that this side here, for example, it's going to be L cosine alpha, and this is L. So delta H equals L minus L cosine alpha, and you can factor out. Don't impulse is a kick. So if you, for the same change in momentum, like a crash, if there is a crash here and someone is in the car and crash, and there is an airbag, boom, 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 boom. The same change in momentum because you stop from moving. You are moving and all of a sudden you are not moving, there is a crash. If you have an airbag, it increases the time of impact, so it increases the force of impact. Same thing when boxing. If you box someone, boxing, boom, 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 you want to roll over, so you increase the time, you decrease the force. Okay, that's cool physics. What else? And finally, remember that each time you have an inclined plane, we discussed that last time, no matter which way it's going to go up, if it's going this way or if it's going that way, you always have gravity here, opposite. And this is alpha. So it depends which way it's going, right? So if it's going down, if it's going this way, so this is the winner and that will be the loser. So this one is going up, so this one will be the winner and that will be the loser. Now if it's going up, that will be the opposite. T is the winner and G sign will be the loser. So acceleration always toward positive, and you have to do the free body diagram. So don't forget work can be negative, and so if you do an equilibrium, last thing, if you do an equilibrium, the like clockwise equals the sum of the counterclockwise, then the units does not matter. So if you have pounds and pounds, it's okay. Only if you are asked to find the torque, then the unit will be Newton meter. So torque applied by a force about the axis of rotation. So it's always exerted by a force about an axis of rotation. The unit is Newton meters. But if you have an equilibrium, the unit doesn't matter, because if you want to convert to Newton, you multiply by something here and you multiply by the same thing here. That doesn't have to be the mass. You like K and you multiply by K, so the unit doesn't matter. Okay.